When you hear the term futuristic, we often think of science fiction and transporter beams, etc. We don't often think of the term SQL. The reason I want to talk about futuristic SQL is many of us think of SQL in three simple ways. And those three simple ways are select, from, where. But in the next 30 minutes, I'm hoping to convince you that SQL is indeed a futuristic language. My name's Connor McDonald. If you want to reach me, you can get me on Twitter, or you can reach me via my blog, or if video is more your thing because you're watching a video right now, then you can get me on my YouTube channel, Connor McDonald Oracle, where I talk about anything and everything to do with the Oracle database. Now, I want to stress, when I talk about futuristic SQL, this is a key point. This session is not about me being a bit of a smarty pants. SQL was always meant to be an easy to digest and easy to understand language. So there's no point in convincing you about SQL with ridiculously overcomplicated examples. The reality is we can do anything and just about everything with SQL. And just for your entertainment, I'll give you a couple of examples of things that we probably won't dwell on too long in this session. Here's the first 20 lines of a piece of SQL, followed by the rest of it, so it's easy to read, written by a community friend named Anton, a very smart guy. And what does it do? Well, you're probably familiar with the Sudoku board. It looks something like that. If I could rephrase that grid into a string in which I could pass into a SQL statement, that SQL statement you just saw will actually solve the Sudoku board, simply with brute force. That's very, very impressive. If you're looking for something a bit more artistic, here's another SQL statement, a much more densely packed one, written by another community member named Rob. You run that on your local machine, and guess what happens? You get something very artistic. You get the Mona Lisa. But let's be real. This is the percentage of you that probably need to solve Sudoku as part of your development job, or, for example, produce the Mona Lisa. The reality is, as developers, we spend the vast majority of our time dealing with the databases to get real stuff done, to solve the needs of the businesses and the business functions that are demanded of our applications. So this session isn't about showing you the Mona Lisa or solving Sudoku. It's about getting real stuff done. That's the emphasis here. Now, I'm going to do it in a slightly different way. I'm going to tackle this from the perspective of my typical weekend, what I do as a parent. And I'm going to encapsulate my weekend from a SQL perspective. The first thing I have to do is take my son Max, that's Max there, to his basketball game. Now, at the basketball game, they record things like the team points and the player points, etc. But I wanted to get a little bit more detail. I wanted to capture the moment every time one of our players in our team scores a point. So what did I do? I headed over to one of our free cloud offerings and simply whipped up a simple application running under Application Express. I called it Game Capture. Every time one of our players scores a point, I simply record the name, the timestamp, and how many points they got. So at the end of the game, I have a table which has captured all the details for some further analysis. A simple question that might come out of this is, well, I need to get meaningful information at the end of the game. I want to see what each player scored. That makes sense. But I also want to see the obvious things like subtotals. Show me the quarter by quarter subtotals. And if we want to know who won the game, obviously we need the grand total at the end. An obvious way of doing it would be to run three queries. There's the first query returning the points for each player. There's the next query returning me subtotals for each quarter of the game. And one more query to give me the grand total. I can get from three queries down to just two queries using what we call a rollup. A rollup, I would start with the initial query again to get me on my low level of detail. But once I've done that, I can use a group by rollup command, which gives me both the quarter by quarter subtotals and the grand total as well. So I've reduced the number of queries by one, but in reality, from a developer's perspective, that's still a pretty messy thing to deal with. I've got two data sources, one being the detail, one being the subtotals and grand total. So when it comes to render that in a meaningful fashion, I need to work my way through the detail and then know that, oh yes, this is the end of quarter one, so grab the quarter one subtotal and then move back to the detail, etc. It's more complicated for me to actually do this. Can we get from 2 queries down to just a single query to actually achieve this goal? Yes, we can. Knowing that the row num facility is a unique number for each row that comes out of a result set, we can use row num combined with group by rollup to get all the totals and the subtotals and the grand totals that we need in the order that we want to see them on the screen. Running this query, I get the low-level detail, then I get the total quarters, and then at the very bottom, I get the grand total. And they're laid out in the logical order that you would expect them to see in. Any kind of totals you want with a single trip to the database is pretty much possible. You can, for example, do a group by cube. Group by cube takes elements and it will do all the various permutations of subtotaling that you require based on those elements. For example, I get subtotals by player and quarter, and then I get subtotals for just the players, and then I get subtotals for just the quarters, and then I get the grand total as well. All the permutations of elements inside the cube are calculated. If I don't want all the elements, I can actually control exactly what particular subtotals I would like to get using the grouping sets operator. In this case, I'm using grouping sets, and I want subtotals by player, and then I want subtotals by quarter, and then I want the grand total, so I get to be selective about exactly what aggregations I want to get from my single trip to the database. All of these could be combined with row num if desired to get the low-level detail as well. And just in case you're wondering if we use these internally, yes we do. If you've ever done a faceted search on Application Express in the more recent versions, we use the grouping sets operator. That way we don't have to do multiple trips to the database to get the information, and similarly Application Express doesn't itself have to laboriously go through each of the rows and manually pick up subtotaling information as it's going. Once word gets out that I've started collecting data about all the low-level point scorers, I start getting emails from interested parents. Here's one from Susie Parent, and she says, "Hi Connor, I saw the report you gave to the coach. It would be cool if we could get that detail broken down." Now, she says for each player. I think that's the politically correct way of saying I'd like to see the detail for my own child, which is totally fine. So let's explore that a little. To get information on a quarter by quarter basis, I have to generate those quarters, quarter 1, 2, 3, and 4. I can do that with a simple connect from Joule. That then needs to be mapped to the data I've collected for each game, every single point score by every single player. Now, if I want to get player results by quarter, that's just a conventional outer join, one that's been around for a long time in most relational databases. I would simply choose my list of quarters 1 through 4 and then outer join that to the point scoring. And I effectively had brought the quarter now into the equation. The devil here is in the detail. If I look, for example, at the players Max and my own son Max, then you can see that because there were some quarters they didn't go on the court, or they didn't score, for example, in that particular quarter, we haven't got a figure for them. We can see Matt's only there for quarters 1, 2, and 4, and my son Max is there for 1, 3, and 4. We've missed some data. The data in relational tables is sparse. It doesn't get invented for us on the fly. What we'd like to do is have quarters 1, 2, 3, and 4 for every single player. In reality, when it comes to joining, we would then need a copy of that list of 4 quarters for each single player, depending on how many players are in the team. Obviously, we don't know that in advance, whether there were 7 players or 5 players or 9 players, because we only work that out once we've actually captured all the information at the end of the game. A partitioned outer join solves that complexity for us. A slight modification to our query, simply adding a partition by clause along with our outer join, solves the problem of the sparseness of data. Campbell's results, he played in every single quarter, so his results are unchanged. But now when we look at Matt, for example, we can see that in the quarter he missed, quarter number 3, we've actually added a row and he scored 0 points, and similarly for my own son. Of course, the most important thing here for me is, why didn't the coach put my son on in that particular quarter? But that's another story. One of the nice things of being able to inflate data where the data is originally sparse using things like partitioned outer joins is when it comes to rendering that information on, say, Application Express or any kind of reporting facility, then we don't have to worry about missing rows. We will always get, in this example, the 4 rows, 1 for each quarter, even if players did not play. That makes breakpoints and stuff like that much more aesthetically appealing when it comes to reporting. The next emails that come in come obviously from the coach. This is Mary, the coach. She says, "Hi Connor, we have a new child, a new boy who wants to join the team. She doesn't know much about him, but she knows that he gets about 13 points per game. Where would that rank him in the existing team members in the team based on their current results?" Now, we could easily do this with a simple eyeballing. We could simply print out the points per game for each player and simply cast our eye down along the list and sort of make a rough assessment of that he fits in a certain spot in terms of his point scoring potential. But can we do it with SQL? We can. We can use a thing called hypothetical analytics. Using a ranking function, for example, I can say, show me the ranking of the points of 13, that's the number inside the parentheses there, within the point scores for this table. So across the entire table for each player, it actually says he would rank third. So if he averages 13 points per game, he's probably going to sit about third in our points rankings on a game-by-game basis. As I mentioned, that's probably just as easily done with eyeballing. But, for example, what if we say if he averages 13 points per game and therefore about 4 points per quarter, where would he rank on the players on a quarter-by-quarter basis? And that's a trivial change to the SQL. Simply adding a group by, because we have the rank within group clause, now shows me that on quarter 1, he would be probably our 5th ranked player. On quarter 2, probably our 4th ranked player. It's very easy to extend these hypothetical analytic examples because of the flexibility of the SQL language. Once basketball is done and I've taken Max home, it's then time to throw my next son, Aiden, into the car and he plays Australian rules football. Not to be confused with English football or soccer. This is a game played pretty much only in Australia. If you look it up on YouTube, it's just a very violent game of keepy-off. The demands of Aiden's football coach for data analysis are a little bit more complicated. Once he discovered I was collecting data, he sends me things like this. Find the total goals scored per player, then find the average of those goals, and then list those players who got above average. And he obviously uses that for some sort of analysis after the game. And I have to do that in SQL. That leads onto the topic of common table expressions, or you may know it as the with clause. And the with clause is, in its simplest form, a way of giving a meaningful tag to a piece of SQL. For example, here I've got a simple SQL, select the quarter, some of the goals from my football team group by quarter. I can use what's called a with clause to give it a useful name, like subtotals. Once I've got that thing called subtotals, I can then query it, select star from subtotals. At which point you're thinking, well, what's the benefit? I've simply gotten more code now. I've had to write more SQL for the same result. Well, I view the with clause as a fantastic mental model for developers. Don't get me wrong, relational is a rigorous mathematical algebraic model. As a result, relational is also the dominant model in the database world. But let's be honest, relational can be a little bit complicated sometimes as well. Now, don't get me wrong, that's not our fault as developers. I blame this guy, Mr. Cod, the man that first put the relational theory together. He had things like, in his white paper back in 1970, data is represented as mathematical n-area relations, and n-area relation being a subset of the Cartesian product of n domains. I don't know about you, but when I first read that, my first reaction was, I have no idea what that is on about. For me, databases were always just spreadsheets, but bigger. Eventually, I learned a bit more about relational theory. One of the challenges for developers when they first get involved in relational databases is developers generally have a procedural approach at tackling problems. They like to tackle things in a step-by-step fashion, but relational is not that. Relational is about tackling things as a single set operation. How can I take a relational challenge but still tackle it step by step? That's where the with clause really comes into its own. Let's revisit that same requirement, but in a step-by-step fashion. So first, find the total goals scored by each player. Well, that's a simple requirement. I can write an SQL just to solve that task. There's my player total, select the player number, sum of goals, goals per player, and I'm going to call it player total. The second step is with the average of those totals. So I need to find the average of those player totals. Well, I can write a query just for that. It's just select average goals per player from that thing I just created, player total. And then the final step was now list those players that got above that average. That's just a simple join between my player totals and my average goals. And there's my result. I can bring those 3 steps together into a single SQL statement. This is the very cool thing about the with clause or common table expressions. We took a programmer's approach. We said, there's a big problem. Let's break it down into small bite-sized chunks and solve them. But we still ended up with a relational solution, a single SQL that does the entire task. We simply pass that on to the Oracle optimizer and it will come up with the best way of running that SQL statement. This is also great for code reuse, and that's one of the things that often gets bashed into us as developers. We always get told, make sure you take advantage of code reuse. Modern applications nowadays are all interested in JSON. It's become the de facto data exchange mechanism. But of course, let's go back to our partition data join example, where I had a query like this, which obviously returns me relational data, returns me rows and columns. A modern application that is revisiting this data might say, well, actually I need it as JSON. One of the beauties of the with clause is I don't have to rewrite this SQL from scratch. I'll just treat that relational data as my raw data, hence I used with raw data, and then I can use some of our JSON facilities available in the database to simply cast that relational result into JSON. So rather than getting rows and columns back now, I get a JSON array, and that's going to be much more useful for modern application requirements. Now that basketball is done and Australian rules football is done, sadly my boys come home and they are starving and they need feeding and they need lots of food at this particular age, so I have to head down the shop. One of the challenges of when I go shopping as I get older and my back gets sore from too many years of sport is I want to be able to divvy up the shopping bags such that they all have the same weight so I don't get overbalanced. When the requirement is divide the shopping equally into 4 bags, well, here's my raw data. I've been to the shop, I've grabbed some milk and some bread and some dog food, etc. But I've got 4 bags. How do I best carve up that information such that I get 4 equally weighted bags? Therefore, I don't topple over, hurt my back, etc. as I'm making the long walk back to the car. SQL can even tackle these more abstract problems. Now, it requires a little bit more syntax because this is a much more complicated problem. But let's build it up bit by bit. What I'm looking for is a sequence of 4 bags. Bag 1, bag 2, bag 3, bag 4. I have 4 bags. I don't know what's in them yet. So I need some rules as to how I'm going to allocate my shopping weights into those particular bags. When it comes to deciding which bag to use, probably the first rule I would apply is, well, if the bag is empty, if the bag currently has nothing in it, I should put something in it straight away. And eventually over time, I will obviously use up all the bags in this fashion. So if a bag is empty, it's the obvious candidate to put this particular shopping item I have in it into the bag. But once obviously each of the bags has at least 1 item in it, now I need to start making decisions as to where to put the next item. With the current item I have, before I put it into the bag, so I need to remove its weight, if the bag before I put this item in is the lightest of all the other bags, then that would be the logical candidate to put this particular item into. So I put it into bag number 1. If it currently, before I put this item in, is lighter than all the other bags I have to consider. If I apply that pattern and repeat it for the other bags as well, I end up with a query that looks something like this. The keyword here is the term match recognize you can see on line 3. That is telling the database that this particular SQL is what we call a pattern matching SQL. It's matching a set of rules that you saw defined on the previous slide. When I run this with my shopping as input, I get this as a result. It might look a little bit cryptic, but if I can focus your attention onto the very last line, you can see those 4 columns, bag 1, bag 2, bag 3, bag 4. I've nicely balanced the weights across the 4 bags. Now, how do I turn that into something nice and meaningful in terms of how to give myself how I should order these items? I can use the with clause we learned about a second ago to take that data you just saw on the previous slide as input, and I can take advantage of another SQL facility called list aggregate that will take a set of rows and concatenate them into a concatenated string in order to give me something a little bit more readable. The result of that is the following. One row for each bag telling me that bag 1 takes the butter, the deodorant, the eggs, and the gin for 3.5 kilograms. Bag 2 takes apples, honey, ketchup, soda, etc. for 3.6. And there we have my shopping evenly distributed across 4 bags, all done with SQL. At this point, you're probably saying, hold on a second. Cast your mind back to the first slide where you said you weren't going to hit us with ridiculously complicated code. You said the code was going to be easy, and that doesn't look so easy. Or you might be thinking, well, that's great for 4 bags, but what if I have 3 bags? Now I have to handcraft a different SQL to handle the 3-bag situation. Or you might be thinking, well, I don't do a lot of food shopping. I don't have children like you. I just go to the hardware store. What if I want to do that same query against the hardware store? That's where we have this facility called SQL Macros. I will concede that that example of SQL there was starting to border on a little bit on the complicated side. But maybe if you've got a particularly proficient SQL developer inside your organization, you can give them the task of writing the SQLs, and then you can use SQL Macros to make that readily exposed in a more simple form to other developers in your company. Let's explore that a bit further. SQL macros are effectively code or SQL that gets to modify or change the SQL you present to it on the fly at runtime, while still remaining very secure. Here is a fairly lengthy piece of code, but I've called this function pack and carry. And probably the only real key things that you need to be worried about here is it takes in the table name and it takes in the number of bags you have. What we're doing here is the first page of this code is building up the list of rules that we explained before in terms of how we decide on what weight goes into which bag. We're building it up as a string. That string will then be inserted into this template you can see here. And you can see this template has a match recognized keyword. We're building up that same match recognized SQL that we saw in previous slides, but we're doing it dynamically. The joy of doing it dynamically is now that function can be made to do all the work of the complicated SQL at runtime. Thus, to replicate my original SQL, I simply do select star from pack and carry, and I pass in the shopping table, and I had 4 bags. That's the original example, now simplified to use a SQL macro. If I have 3 bags, I simply pass in 3 for the number of bags, and now I get a fresh result where the weights are evenly distributed across 3 bags. Or if I don't go shopping, but I go to the hardware store and I've got, say, 5 bags, then once again, just simply call pack and carry, pass in the hardware table and pass in 5 bags. And now I've got my chainsaw, my power washers, etc. distributed over 5 bags instead of 4. Finally, after basketball and after Australian rules football and after feeding them, hopefully they'll retire to the couch and I finally get a bit of me time. When I want to spend some time, doing a bit of exercise, I like to swim laps. I'm not a great swimmer, and I normally try average about 60 seconds per each 50-meter lap in the local swimming pool. And for me, I'm looking for consistency here. And when I time my laps, I get this kind of output. I'm trying to stay exactly on 60 seconds all the time, but I vary from lap to lap. Sometimes I'm a bit too fast, sometimes I'm a little bit too slow, etc. When I record this in a table, you can see this is sort of my progress as I do, for example, a 12-lap session. You can see I was 58 seconds. I started that a little bit too, overcooked, but then I slowed down and I'm trying to keep it around 60 seconds per lap. But really what I do is I don't want to be averaging 60, but being all over the place on a lap-by-lap basis. I'd like a nice, consistent form of 60 seconds for every single lap, if possible. What I'm really trying to say is, am I on track? Am I keeping on track on every single lap rather than being very, very variable? One of the things I can do is start looking for patterns. For example, on laps 1 through 4, if I add up those 4 times, I actually was slightly under, slightly over, but when I added up the deltas, I ended up with 0 as a net result. Therefore, I averaged 60. I did the same on 9 through 12 as well. For the first 4 laps, last 4 laps, I was doing pretty well. The question is, can I solve this with SQL? And once again, I can use the match recognize, the pattern matching calls to give me this. We're hopefully familiar with it now. So you can see it picked out that yes, 1 through 4 got me on an average of a total sum of delta of 0, which means I averaged 60, and laps 9 through 12, I did the same. But here's the great thing with SQL. SQL, because it's obviously correct, will pick out things I may have missed, and maybe you missed it too. In reality, laps 2 through 10 actually sat on an average of 60 when I added up all the plus and minus deltas as well. And SQL can also reveal that to me. Simply by adding the after match, skip to next row, I effectively find a pattern and then skip to the next row to start again. So 1 through 4, yes indeed, was a net 0. But also 2 through 10 was a net 0. Even 4 through 10 was a net 0. And finally, as we saw before, laps 9 through 12 were also a net 0 for me. So once again, the enormous power of SQL shows me all the ways in which I kept on track. Now it's time at the end of the weekend, after doing all that driving, I need to refill the car. Sometimes, even though the car is running a bit low, I do my best not to refill it on the weekends. I'm not sure what the case is around the world, but in Australia, certain days have certain discounts on the fuel. There are certain days you should always try fill up because the petrol is the cheapest. And given the exorbitant price of fuel nowadays, you can get some good benefits by making sure you refill on the cheap days. I now keep a log of when I actually fill the car and how many litres were in the car at the time when I filled it. It's not just a case anymore of filling it when it gets to empty, because sometimes I'll fill it even if the car is nearly full because it's a cheap day. This was a useful plan until I read to the owner's manual, and it said it's always good to empty your car out totally because you'll actually end up with cleaner fuel that way. And they even gave me a little spreadsheet which shows you how to work out the impurity levels in your fuel. When the car starts off as empty, you filled it from percent full of 0, it says simply take the number of litres you've put into the car, take I think 0.05%, and that's the level of impurities you're going to have in the car. That's how you calculate your initial amount of dirt in the fuel tank. The problem is if the car is not empty, then when you refill it again, you need to take the impurities that were already in the car, so the previous calculation of impurities, and then multiply that by the litres it already had, and then there's a new calculation for the litres that are going in. You only work out the information for purities when the car is empty, but if the car is not empty, then you have to use the previous calculation, which of course we don't have yet. We actually need to do a recursive view here to find out the information. I don't know that the dirt will be 2.6 until I've calculated that the dirt for the previous refill was 2.25. I need recursion, and I need it in SQL. First of all, I'm going to use a row number analytic to give myself a unique sequence number for every single row in the table. Then, using a with clause like we've seen before, I can use that new query as a source into my level of dirt calculations. The first thing I'm going to do is have a with table clause here called results. The first part of my results is I'm going to do a dirt calculation for the very first row when I filled up from empty, and that's where sequence equals 1. I can do a simple dirt calculation because I saw it was just 5% of the number of litres I put in. To do a subsequent dirt calculation, I need to refer back to this table of results. And that's what I can do with a recursive with clause. You can see that the query actually takes the results table as an input and joins to itself, even though it's its own table. We have a recursive relationship within the with clause. It mimics the recursive relationship we saw in the Excel spreadsheet. And when I run it, I get the same results out of my query as I did with the Excel spreadsheet. Let's wrap up now before our time runs out. I called this topic Futuristic SQL, but in reality, I think of it more as just intelligent use of SQL. If we take a quicker look at the features we covered today, you might think they're brand new, trailblazing, pioneering features, but they're not. Some of these have been out for over 20 years. In fact, most of them have been out for decades inside Oracle. In fact, the only one you could argue is even remotely futuristic is SQL Macros, which came out a year ago. So all of these things are robust, tried and tested solutions that have been available for many years in the Oracle database. We see them as futuristic because many of us don't use them and haven't explored them fully. I hope this session has proven you that SQL is indeed incredibly robust, super cool when it comes to the ability to solve problems, and therefore incredibly powerful. If you can really embrace the power of SQL, you're going to end up writing less code in your applications, and you're going to end up with faster, more scalable applications. If you're fresh to SQL, it's never too early to get stuck into it. This is many, many years ago. My first son, Max, we got him stuck into SQL as fast as we could so he could become fluent at a very early age. That means it's your turn to do the same. I've put here a few resources here. We've got hands-on labs in which you can learn SQL. If you want a scratchpad to write SQL, you can go to livesql.oracle.com. And when it comes to all of the various free facilities you can use within the Oracle database, head over to developer.oracle.com/free to get a list of incredible resources available to you for absolutely no cost. We're done. Please stay in touch. Hit me up on Twitter or on the Q&A if you have questions about SQL or the Oracle database. Until then, hopefully this has inspired you to get out and broaden your SQL knowledge and build mind-blowingly fantastic applications. Bye for now.